Hello, welcome back. There are two handouts today, one of which is the real handout number 25, which is problem set number 4 solutions. The other one is a fake handout number 25, which is supposed to be handout number 26, which is a set of lecture notes on I/O, which we'll probably not get to today, but we'll start next time. The handout numbering scheme is a pipeline, and that pipeline had a read after write hazard that we weren't fully interlocked for, so we executed incorrectly. So in fact, I don't know what numbers are going to be on the handouts that SITN gets, but if you get two number 25s, then the lecture note set is actually number 26. Okay, last time we were talking about virtual memory, but I would like to back up just a second to go back and revisit some things about pseudo-associative caches, some questions that came up. So let's look at that for a second. One is the way we compute the average memory access time. Now remember, I'm sure you're all familiar with it because you're doing it for the programming assignment. Pseudo-associative cache is the scheme where in a direct map cache you look at one place for the match, and if it's not there you look at another place for the match, and if it's not there then you miss. And what I had written down as an expression for the average memory access time was something like this. It's the time it takes you to do a hit, which is probably one cycle based on doing the first test at the first location. And then there's some time based on some number of time that you miss in that first shot, and that's the miss rate that you would have gotten had it been a regular direct map cache, times some cost to do the second probe. So the model is you try hit. If it works, you're done. If not, then this percentage of the time you did that, and you had to, that's also the misdetermination time to see whether or not it's not there, and then some percentage of the time, which is the miss rate in a direct map cache, costs you to do the second probe. And then if you miss that, as a third phase, there's some percentage of the time which, if this really is like a two-way associative cache, it's the miss rate of a two-way associative cache at the same time, times the miss penalty to go to disk, or to go to main memory. And it's a kind of three-step process. Now what the book actually derives is a slightly different formula that shows this miss ratio, or that uses for the miss ratio times the cost of the second probe, the miss ratio of the direct map cache minus the miss ratio of the two-way cache. And really what that's doing is saying that if you miss in this second probe, then it didn't cost you anything because you've already gotten started on the access to main memory. So that's a different model for the way the pseudo-associative cache is working, that says, well, first you try the first location, and then in parallel you try the second location and also go to main memory, assuming that the first one might miss. So it's a kind of parallel operation. Depending on how you implement the pseudo-associative cache, you might use one model or the other. I think this one tends to be more realistic. In general, for these caches, we've not assumed that you sort of speculatively execute both paths and try to do a hit in the cache and at the same time begin accessing main memory, assuming you might do a miss. So if your model is that you do these things in sequence, then you get the expression that I originally showed. If your model is that you start the two second parts in parallel, the second probe and the access to memory, then you get the expression that the book had. Any question about that? The other thing I wanted to do was to correct an answer I gave to a question that was asked. Well, I didn't tell the whole truth. And that question was whether or not the algorithm as originally described actually works. Remember, we talked about the use of the rehash bit to get better performance in this pathological case where alternating accesses would cause us to do a miss on every access. The question is, if you don't do that, does the pseudo-associative cache work? And the answer is, well, almost. You've got to make one minor modification. Let's look at this pseudo-associative cache. Remember, the cache has a tag part and a data part. And because of this high-order bit flipping we're doing, we've essentially divided it into two halves. And we try first for a match in the first half, and then if we don't match there, we look for a match in the second half. Well, the virtual addresses that we're, or the memory addresses that we're using to reference this has a tag part in it and has an index part in it. And we're using the index part as the subscript, if you will, into this array that says which entry to look at. And we might pick an address that maps into this location, and we put its data here. We might pick another address, and let's say that it initially maps into the pair of this item, which is to say that these indexes are the same except that they differ by the high order bit. So this has a 1 in the high order bit, and this has a 0 in the high order bit. Well, let's say that we wind up rehashing this entry into that entry for some reason. And let's further say that the rest of these tag bits are identical. If that's the case, then by looking at this entry in the cache, how can you tell whether it's this address, or the data for this address in that cache location, or the data for this cache, for this address in that cache location that happens to be in its alternate location? The answer is you can't tell. And if that's the algorithm that you use, then the cache is broken. But it's easy to fix, and the way to fix it is just to include in the tag the next bit in the address, the most significant bit of the index. So if you include the most significant bit of the index as part of the tag in the cache, make it 1 bit wider, then this pseudo-associative algorithm works. Still has the problem we talked about last time, where there are some fairly weakly pathological, only slightly ill cases of addresses that will cause a lot of misses in the cache, and that's why the rehash bit algorithm was invented. Do you all feel comfortable with that rehash bit algorithm? Do you understand sort of intuitively how it works, or do you want me to say some words about it? Yes? Okay, let me sort of describe it a little bit. I don't want to describe it in all gory detail, because then it's not fun for you to figure out on your own. Basically, remember, the first hash function is B of A. So we look in location B of A in the cache. Now we've also got this R bit that now tells us whether or not whatever is residing at that cache location is in its primary location. So if we're looking for address A and we look at B of A, and it also happens to be the case that the R bit is 0, then we know that we've got a hit, because we've matched in its primary location. We know that it's one of the two locations because B of A maps there, and since R bit is 0, we know that it's a primary location, and it can't be somebody else who mapped from a different location and wound up here. Now, one of the invariants of this whole process, which you should keep in mind, is that the two R bits can't both be 1. The two R bits of two related locations can't both be 1. So that of the two locations that are related to each other by having a higher order bit difference, both of them can't be occupied by somebody in their alternate position. And if we guarantee that, then you'll see how this algorithm works out. So let's say that we're not in our primary position, or that the guy who's in there is someone else. Now we look to see, is he rehashed from an alternate location? Right? If the guy currently in B of A is rehashed from an alternate location, we don't have to check our alternate location, because if we were in our alternate location, then both of those entries would be rehashed. They would both have the R bit 1. So in fact, if we're not in our primary, but somebody else is in our primary that's rehashed, then we don't have to check our secondary location. Right? And we can just replace ourselves, basically put ourselves in the place where B of A is, and then we're primary, so we set the R bit equal to 0. With me so far? Okay. So now we know that somebody is in our primary location, and he's a primary, so we could be in our secondary location. So we have to check our secondary location. and we check to see, is there somebody matching our index in the secondary location? And incidentally, for it to be us, the R bit has to be 1. If that's the case, then we have a hit, but we want to swap to get 1 cycle access time if we happen to make an access to our location next time. Now remember, when you do the swap, you've got to think about whether or not you need to change the R bits in order to keep them correct. It's part of what you've got to get right in the programming assignment. If it's the case that that either somebody else's tag is in that location, or the R bit is 0, meaning it's somebody's primary location, it can't be us. In which case, we've got to throw him out, so we replace whoever is in that location, which is our secondary location, and then we swap to make us primary. And again, you've got to watch the R bits to make sure that the R bit is on for people who are in their alternate location and off for people who are in their primary location. And this will guarantee, too, that there are no, of the 2 items, there aren't people occupying it in their secondary location in both slots. Does that help any?
What are those operators?
What are those operators? These operators?
Yeah, they
no,
or
those,
and and.
Those are and.
Both of them are and?
Yeah, I guess in C notation it would be ampersand, ampersand, or something like that.
It's hard to see it on the screen.
Okay, sorry.
When did you set RB to 1?
I'm sorry?
When did you set RB to 1?
I'm not showing you. Sort of intentionally, and I don't want to draw this algorithm in such precise detail that all you need to do for the programming exercise is, transcribe it from a flowchart into C without really understanding what's going on. I think it's important to understand how this algorithm works, and one of the details that I'm sort of fuzzing over here is where you set or reset the R bits in order to guarantee that this algorithm is correct. I know, it's mean of me. Any other questions about caches and pseudo-associativity and such like? Okay, now we go back to virtual memory. Remember, virtual memory was this technique which was originally designed so that programmers could get more virtual memory than they had real memory.
Hello?
Yes?
Question, please.
Yeah.
Did we ever had a chance to cover the memory interleaving and DRAMs and SRAMs?
No, it's in the notes, and I want to get finished with virtual memory, and then we'll come back to that.
Well, thank you very much.
You're welcome. So virtual memory is a way to make big virtual addresses into small physical addresses, and it turns out it also acts as a cache. And the sort of general scheme for translating virtual memory addresses into physical memory addresses was something like this. This is a kind of typical multi-level memory address translation where you divide the virtual address into different parts, and you use each part to look up an entry in a page table, which either points to another entry in a page table, which might point to another entry in a page table, which eventually will point in main memory to a physical page. Or have the entry marked saying that that page doesn't exist, or have the entry marked that says that page exists but is not in physical memory, it's out in main memory. Somebody pointed out that I kept referring to this as a 32-bit virtual address, and that 10 plus 10 plus 10 plus 13, in no base that they could think of, added up to 32, which is true. The DEC Alpha, which is what this scheme was modeled after, actually has a 64-bit virtual address mapping into a 32-bit physical address. And in most current implementations, they're only using the first 43 bits of that virtual address. But as programmers write programs bigger than 2 to the 43, they may eventually extend the virtual address translation to use more of the 64 bits of virtual address. So that solved the first problem, which was that the page table was enormous. So now the page table can be much smaller because it only maps the part of the virtual address that's really in use. But the other problem was that after having devoted all of our time to being very clever at having one cycle memory accesses in many of the cases. Now for every memory access, we've got to do 3 other memory access to access the page table translation. So the solution to that was yet another cache. The address translation cache, or as IBM called it and everybody else does too, a translation look-aside buffer. And it's typically a cache that is very fast, is designed to have an extremely low miss rate. Much less than 1% is desirable. 0.1% is more like what you want. So it might have someplace in the range of 8 to 1,000 entries. It only needs to hold translations for pages that are actually in main memory. Pages that are not in main memory, that are either invalid or are written out to disk, obviously don't have to be translated as part of this fast process, because in any case it's going to take you a long time to process it. So it's only a subset of the pages that are actually existing in main memory. And in order to get the miss rate down as low as possible, these caches are typically fully associative or very close to fully associative. Now what happens when it misses? Well, it's certainly not as bad as miss in virtual memory going to disk. In fact, it's a relatively small miss penalty, something on the order of 10 to 50 cycles. After all, basically what it needs to do is to look up entries in one or more page tables. Those page tables might in fact be cached as well, so you might be doing cache hits in doing the translation process. Now, in fact, there are 2 different schemes. The original address translation schemes, as done by IBM in their mainframes, were all done in hardware. When the miss occurred, in fact, it trapped to a piece of microcode used in the implementation of the machine that would do the hardware lookup in the page tables. And there are a bunch of other machines as well that continue to do that. x86 has hardware translation look-aside buffer processing. But you don't have to. If you carefully hone and tune the interrupt process for translation look-aside buffer misses, you can do it in software without causing too much of a miss penalty. So MIPS, in fact, does that. One of the advantages is that if you do that right, then in fact the page table structure and the algorithms you use for looking up things in page tables is not built into the hardware. It's only indication of, it's only a software artifact, so you're free to change the page table structure if you wish, although it's unlikely certainly any user would ever want to do that. It's an interesting area where the interaction between hardware and software can sometimes get you into a little bit of trouble, and I think I brought it actually. There were a couple of months ago there was paper published in the ACM Transactions on Computer Systems talking about, in fact, the MIPS TLB system and how it works in its memory, in its software-controlled page table, TLB MIS scheme. It turns out it's not quite all left to the software in the MIPS processor. In fact, what they do is they divide the TLB into 2 different sections. It's a 64-element fully associative TLB, and the first 8 entries are intended to be dedicated for the operating system. And when you take a TLB miss, the hardware gives the software interrupt process some assistance in deciding which TLB entry should be replaced. Remember, this is a fully associative cache. We've got to do something like LRU, if we're lucky, to figure out which item to throw out. Well, in fact, what the MIPS processor does is not LRU, it's that random algorithm that we discussed before that turns out, much to my chagrin, to be almost as good as LRU in lots of different cases. But the model for the MIPS was that those TLB entries that get thrown out are only for user processes, not for kernel processes. In fact, the MIPS has a multi-level page table, much like the Alpha. If we can zoom in on this. This shows a level 3 page table going to a level 2 page table, going to a level 1 page table for user pages. It turns out they have another path where level 2 page table entries point directly to pages for the kernel. And those pages don't participate in the TLB discard policy. These are the 8 TLB entries that it doesn't give you any assistance for in doing TLB entry replacements. Well, that worked great because this was all designed for an Ultrix-like system, and it turned out that the kernel mapped by those 8 TLB entries fit perfectly. The 8 TLB entries that were sort of fixed or intended to be fixed mapped perfectly onto the size of the Ultrix kernel. Then they ran a different operating system, and it all broke down. And in fact, they show some numbers here for what happens as they move from one operating system to another. We can probably just look at this part here. This is the way they originally designed the system. For Ultrix, these are level 1 user TLB misses, and there are 9 million of them, a lot of them. And then level 1 kernel misses, those 8 special TLB entries that were dedicated to the kernel, there were many fewer of them, 135,000 misses. In this case, the hardware was well designed to match what the software was currently doing. But then you run other versions of Unix-like operating systems, like OSF and various flavors of Mach with and without the Andrew file system, and suddenly the number of TLB misses for the kernel jumps up by more than a factor of 10. It goes up from 135,000 to 1.5 million, or 2.5 million, or 2.7 million, becoming a significant fraction in some cases of the overall TLB misses. So I guess the moral of this story is, if you're going to design your hardware to take into account a particular software environment, you've got to try to anticipate as much as possible the natural evolution of that operating system, and don't build something into the hardware which will come to bite you later on. I think in the later versions of the MIPS processors, they changed that strategy. They changed, does anybody know the details? They changed the number of TLB entries. They changed the number of, perhaps I think it's at least one of the proposals in that paper is to change the proportion of TLB entries that are allocated to kernel space versus allocated to user space, to try to get around the problem that the match between the hardware and the software isn't what it used to be. This is what a translation look-aside buffer looks like. It's a kind of standard cache in the sense that it uses the virtual page number part of the address to compare to the virtual page number tag in the cache. It's typically fully associative, so all of these entries are compared at once to the virtual page number, and if there's a match, there's a hit, and the physical page number is part of the cache, is concatenated with the page offset, which flows through unmolested. It doesn't participate in the TLB process. Now, there are other bits that we might want to put in here. Certainly there needs to be a valid bit saying whether that particular cache line is valid. Notice now that we're doing all of the references to physical memory without looking up things in the page table. So other status bits that are in the page table may have to be put into the translation look-aside buffer, like, for example, write protect bit. If you need to check whether this particular process has the legal right to modify a page, that's a bit that used to be in the page table. The page table isn't accessed anymore, so you've got to add something to the TLB to be able to do that. Another thing you might want to consider adding to the TLB is a dirty bit for the purpose of doing the LRU page, for being able to dump pages out to disk when they need to be replaced. You need to keep track of which pages are dirty, and if we're not making those changes in the page table, we better make those changes in the translation look-aside buffer, and then later have a way to communicate that information back to the page table and eventually be used to write memory out. Okay? That's TLBs. And before that, we talked about caches. And the interesting question is, how do the two of them interact? we have to do a translation process, and we also somehow have to look in a cache to see whether we can avoid going to main memory. In what sequence should we do those operations? Well, the one that makes the most sense is that you'd like to treat the cache as just something that makes main memory faster. And if main memory is addressed with physical addresses, then you'd like to address the cache with physical addresses. So you treat this whole subsystem here as basically just a fast main memory. Well, that means you have to do the translation first. You take the virtual address, virtual page number and offset, turn it into a physical address before you access the cache, and then access the cache with the physical address. So the index field that you use for looking up in the cache and the tag field that you use to check to see whether the correct value is in the cache are both physical addresses. That works great. The problem is that it's a serialized operation. You can't do them in parallel. You have to take at least a 2-cycle hit for every memory reference. The first cycle to do the translation, the second cycle to use the translated address to do the cache lookup. So it works, and it's been used by machines like the VAX, but it has this unfortunate property of turning what used to be a great 1-cycle cache hit into a 2-cycle cache hit. So what can we do about that? Well, one thing we can do about that is to decide to do the cache first, put the TLB, the translation process, in front of main memory. And that means that what we're storing in the cache is all based on virtual addresses. We take the virtual page number, take the virtual address, and we look that up in the cache using some number of its bits, which may or may not correspond exactly to the virtual page number, and look up in the cache. What we check to see whether the correct value is in the cache is a part of the virtual address. It's a tag. Basically, the cache is just a way to get fast access to virtually addressed data. And then if it misses, we do the translation to real addresses and go to main memory. Well, this solves at least one problem. It allows us to, in most cases, get back to a 1-cycle memory access. The problem is that there are lots of other problems. And the next slide talks about some of them. One is that, remember, this is a multi-programming environment, and we're running different processes which may be using the same virtual addresses to reference different data. They may, all the users running on this Unix machine may believe that their program begins at absolute location 0. Yet they're different physical addresses. Our cache contains one entry for virtual address 0, so we're going to be in trouble. One way to solve that problem is just to wipe out the translation at the time that a process switch occurs. And in fact, guarantee that that you can't have two identical virtual addresses going to the same physical address. Another way to do that is to include as part of the cache tag an address space ID. I didn't mean here flush the TLB, I meant flush the cache. Right, you've got to wipe out the cache because it's got virtual addresses it's got real data for virtual address 0, and when you switch a process, you've got different real data for that virtual address 0, so you've got to throw out of the cache the old values. Well, one way to avoid throwing it out is to mark the data in the cache with something like a process ID or an address space ID that says, in addition to what virtual address this data corresponds to, which process did it correspond to? So that means when you do a switch from one process to the other, you don't have to throw out everything because virtual address 0 from the next process won't match virtual address 0 from the previous process because the tag, the address space ID part of the tag, won't match. Turns out this is a big win. The next chart shows some data that shows 3 different cases. One is if you're not doing any process switching at all. The second is if you process switch but include in the cache these process IDs so you don't have to purge. And the third is the case where you purge the entire cache. Well, when the miss rate is high, it really doesn't matter. You're going to suffer whether or not you're process switching or using process IDs or purging the cache. Basically, it's terrible in all cases. When the miss rate goes down, though, if you look down here, it shows that including the process IDs as part of the cache tag gets you almost as good as not doing any process switching at all in terms of the overall miss rate. So if you're going to use virtual caches, then including the process ID is a good idea. Now, this obviously depends on the frequency with which processes are switched. If you don't switch very often, then it's not going to have this big an effect.
You mean TLB purge or cache purge over there?
Cache purge. Sorry.
Don't you also have to purge the TLB, though, and for the same reason?
Yes, I guess you would also have to purge the TLB, and for the same reason. Okay, more problems with virtual memory and caches. One is that there's a problem with aliases. If we want to have the same data being addressed using two different virtual addresses, remember we showed that as part of the advantages for virtual memory, that we can have two different processes using two different virtual addresses to get to the same data. If we use virtual addresses as the basis of storing things in the cache, then in fact we'll wind up with that data appearing twice in the cache. So that's a problem. We can either prohibit it, or we can have some kind of a hardware scheme that forces all of the data blocks in the cache to actually represent unique physical addresses, which is a hard thing to do. Or we can begin to restrict the addresses that we assign in either virtual memory space or physical memory space to shared blocks, and I'll talk more about this in a second. The other problem that comes up with caches that use virtual addresses is that I/O devices are typically using real addresses, and in order to access data which is in the cache, they're going to have to do a kind of reverse translation from physical address to virtual address. In a similar vein, the shared memory multiprocessors, you can think of that as an I/O device, basically another process which is trying to access your data in the cache, would have to know about the virtual addresses and invalidate cache entries. They typically know a physical address, which is what they're trying to access, and they would have to, based on those physical addresses, understand what's in your cache, which is indexed by virtual address. So again, it needs a kind of remapping to virtual addresses. Or another scheme you can use is to have in the cache both virtual tags and physical tags at the same time. Physical tags to be used by other processors and I/O devices, or virtual tags to be used by the current process that wants to get one cycle accesses without having to do the address translation. People tend not to use virtual address caches these days. The original Sparks did, and they got around some of these problems by various address restrictions in the virtual address space and the physical address space. I'm not sure whether current Spark implementations use virtual address caches still or not. But there's another technique. It turns out that if we're clever, we can arrange to do the cache access, and at least part of the cache access, and the address translation in parallel. Remember that the virtual address is divided into a page number, which has to get translated to a physical page number, and an offset, which doesn't get translated to anything, which gets concatenated later with the physical page number. Well, if it turns out, and if we can arrange it, so that the part of the address which is used to do the indexing into the cache contains only the bits of the address that are not going to get translated, which is to say it's the size of a virtual memory page or less, then we can start doing the lookup in the cache based on this cache index, which is a virtual address, at the same time that we're sending the virtual page number through the TLB to get translated. And these are operations that roughly take the same amount of time. They're both a kind of memory lookup operation. This is probably certainly associative. This may or may not be associative. Then by the time the data is out of the cache, we've got to do a tag check. We've got to check the tag part of the cache with the rest of the address, but now we can check it with the real part of the already translated address. So what we store in the cache is the physical tag, a tag based on the physical address of the translated address. But we're indexing into the cache using a virtual index, using the part of the virtual address. Another way to look at the memory address layout is that from a paging point of view, we've got, in this case, 19 bits worth of virtual page number and 13 bits worth of page offset for an 8K byte page. From a caching point of view, we've got 19 bits worth of cache tag. We've got 4 bits worth of byte offset for a 16-byte line, and 9 bits worth of cache index. So we've got 512 entries, sets. And we can do this lookup in parallel with the virtual address translation. So we're back to one cycle if you include the tag check as part of the one cycle. So the cache data is now based on physical addresses again. We don't have the problem with aliasing and snooping from other processors and I.O. But this only will work when, well, this is wrong. It only will work when the offset bits or the cache index bits are not needed for the TLB lookup. And that restricts the organization of our cache. It means that the cache size has to be less than the page size times the associativity. Like, this is the size of a page. You can make the cache as associative as you like, but you can't increase the number of sets, because as soon as you do that, then you've started to use as your index an address that might get translated later as part of the virtual to real translation. So in order to make caches large, you have to keep increasing the associativity. This is a scheme that IBM mainframes used all the time, and in fact, in order to keep increasing the size of the cache as main memory increased and program working set increased, they had to increase associativity to 16 times or 32 times. I don't know how far they eventually got before they ran out of money to be able to apply comparators to making associativity very high. And in fact, this is probably the most common solution to the problem of doing simultaneous virtual memory translations and cache lookups. Notice that 21064 we looked at did exactly that. In fact, it limited its caches because they were non-associative, they were direct mapped to exactly 8K for instruction cache and data cache, exactly for this reason. They wanted to be able to do the lookup in parallel. Questions about that? Okay. I just want to hint that, in fact, that's not the only thing you can do. All is not lost if a few of the page number bits are needed for cache lookup. And people have used some clever schemes in order to be able to violate that constraint, basically to have some of the bits being used in the cache be bits that might be translated as part of the virtual address translation. And these are called so-called color bits because they basically try to divide pages into different equivalence classes, and all of the pages with those 3 bits 000 you consider red pages, and 001 might be green pages or something like that. I think that's where the term color bits came from. Basically, it's a way of just dividing the pages into different equivalence classes. And there are several different ways that you can use this. One is that you can decide to restrict the places that virtual pages can be mapped to physical pages in memory. Right? In that case, each page frame in main memory is a different color. And you can, by doing that, guarantee that for those 3 bits, for those color bits, that the virtual address is the same as the real address. That there will be no change in these bits as they get translated from a virtual page number to a real page number. What that gets you is that if you have different page numbers, which will be different places in the cache, then you can guarantee that there'll be different physical addresses because there'll be pages that have a different color and they will have been mapped to a different physical location. Another trick that you can use with the same kind of color bits is to have the sort of opposite a case. Let's say that we want to have different virtual addresses going to the same physical address because we want to do sharing. We want 2 different processes to share the same physical address. And let's say that for process number 1, it has a virtual address which looks like P1, P2, P3, P4. Let's say that these are hex digits or something like that. And an offset 1 and an offset 2. So this is for process 1. And then process 2 wants to be able to get to the same page, but it's using a different virtual address. Let's say P5, P6, P7, P8, and the same offset. And let's say that this is the part that is used for the cache lookup. Well, if you allow those 2 virtual addresses, then in fact they're never going to be able to reference the same data. Even if you made this translation all mapped to the same physical page, there's a problem because these will go, I guess that includes this, these will go to different sets in the cache. Well, one way to deal with that is to, in software, assign virtual addresses so that P4 and P8 are the same. Basically, it restricts the addresses of virtual pages that can be shared based on how many of the virtual address bits are used as part of the cache lookup. And if you do that, you can still have different virtual addresses, at least different in the higher order bits, that share the same physical address, and still be able to do cache lookup and translation in parallel. A little bit bizarre, but it is done. These are the kinds of places where the architecture and the implementation begin to mix in messy ways. In this case, it's more the software architecture and the operating system that is beginning to interact with nitty-gritties in the way the caching and address translation is done in the machine. From a purist point of view, it's probably not the most desirable kind of design space, but on the other hand, it works. And you can't argue with success. Before we leave paging, I guess I need to say a few words about segmentation, although segmentation is kind of out of favor these days. Segmentation and paging are very similar in many ways. One way to look at it is that paging has one fixed page size, or maybe a few different page sizes. It's often the case that a page size is, if fixed, is 4K or 8K or something like that. Some systems allow you to have a choice of, let's say, 2 different page sizes. Sometimes that's useful because if you use a very large page size, like, I don't know, 256K or bigger, you can use that for something that has to be physically contiguous. Like if you have a frame buffer or an image buffer in your machine, which you're addressing with virtual memory. It's not reordered the way normal memory pages are, so by accessing it with one or a few very large pages, you can, for example, take less TLB space. So sometimes a system that allows a small number of different page sizes can be an advantage. Is that a question? No. segmentation you can view as a kind of paging scheme, but where every page has an individual size. Basically, the descriptor, the page table entry, if you will, now called a segment table entry, describes exactly how big that page is, or that segment is, and could be down to the byte level. Could be a 37-byte segment. There are some systems, in fact, that have both paging and segmentation. The x86 is one example that first does segmentation and then does paging. And you can choose to use the machine with one or the other or both. And these days it's more and more that people are using the paging only and not the segmentation. But what are the distinctions? Well, for one thing, paging is nice for the programmer in some ways because it's invisible. Addressing is just by one word, which might be 32 or 64 bits, but it's a flat address space. In the case of segmentation, it's a structured address space. There's a segment part and there's an offset part. And depending on the segment part, the offset part can have different possible values because all of the segments can be different sizes. So it's exposed to the programmer. Now this may be a good thing. For example, I guess that talks about it on the last line here, this may map a model that you have in the high-level language for how objects are to be allocated and shared. And if you allocate or assign an individual segment to each object, and you're free to define what an object is, then in terms of protection and in terms of memory allocation, it may map, the addressing scheme in the hardware may map better to the software's model of what's going on. In terms of page replacement, if we do fixed size paging, it's easy because any page frame in memory is equivalent to any other, unless we're doing the color bit scheme, of course. In the case of segmentation, they're all variable sized objects, so it's harder to do allocation. It's like heap allocation in software systems. They both have memory fragmentation. In the case of paging, the fragmentation is internal to a page. If you want to make your program bigger, you make it bigger in units of 4K or 8K or 256K, whatever your page size happens to be. In the case of segmentation, you can make your program bigger in units of single segments, which might be single bytes. The problem is that the memory fragmentation is external to the segments. When you look for a place to put a segment in main memory, you may find lots of little pieces that are wasted and no big piece which can fit the segment that you're trying to bring in from disk, say. In terms of disk traffic, this is a kind of weaker argument. Paging tends to be more efficient because it's easy to do multiple transfers of fixed size objects. It's also easy to have tables that you can use to look up where on the disk those pages are, and it becomes a little more difficult for segments that are written out to disk because they have variable sizes. Segmentation is on the wane, although it had been popular in the past. As you begin to take segmentation to more elaborate lengths, people have built segmented and machines that have both segments and capabilities that expand the kind of protection scheme that processors are allowed to use, but I think that's all I want to say about that. Any question about paging, segmentation, virtual memory, caches? Do things faster? Okay, now I want to cycle back to something that I think appears earlier in your notes that I skipped to because I wanted to get through the virtual memory stuff. And this was along the theme back when we were talking about caches, about how to make the whole process of looking things up in a cache and dealing with cache hits and filling up the cache from main memory as fast as possible. So these few slides look at main memory itself and tries to figure out how it is that we can make main memory faster when we're accessing main memory to fill up the cache. Well, one kind of obvious thing is to make it wider. Let's say that we have a cache that has a 32-bit path. Remember that my notation here is that lowercase b is bit, and uppercase B is byte. I don't know if I made that explicit, but I figure you caught on to that after a while. Here is a cache that has a 32-byte line, and it has a 32-bit interface, both to the CPU and to main memory, so that when the CPU wants one word, it gets it in a single cycle. When the cache misses and needs to fill from main memory, it needs to go through 8 cycles of 4 bytes each, 32 bits, in order to fill up the cache. So one simple way to make that process faster is to double the width of the cache. So it's got 64 bits in, 64 bits out. It now needs only 4 cycles to fill from main memory when it misses instead of 8. So we've doubled the bandwidth. So this is a particularly good match for caches that have wide lines. Notice now that we've got to choose from the outputs of these cache RAM chips, say, which half we're going to be sending to the CPU. So we've just now added a multiplexer in the path from the cache to the CPU, which increases the hit time. So it's a multiplexer that's in a bad position because it's made the hit access to the cache slower than it used to be. So that's one of the disadvantages of making the memory wider. The other is that all of these data paths suddenly got wider, which costs more pins, more buses, more space, more chip space, or more board space. The other kind of funny argument is that it's almost a marketing argument that it changes the increment in which you can buy additional memory. If each one of these things is a, I don't know, 1 megabit, let's say it's a 1 megabit chip, then you've got 8 megabits or a megabyte of memory, and if you want an additional megabyte of memory, you just add another 8 chips. If you double the width, then you can't do that in increments of 8 anymore. You have to do that in increments of 16. So when your customer wants to buy more memory, he's suddenly got to buy 2 megabytes instead of 1 megabyte, or 16 megabytes instead of 8 megabytes. It makes the choice of main memory more granular than in the case where it was a narrower main memory. That's sometimes a problem. Okay, that's one way, make it wider. Another way is to make it wider, but basically put the multiplexer in a different place. Instead of a 32-bit wide cache fed by a 32-bit wide memory, we have a 32-bit wide cache fed by a 64-bit wide memory. And we assign the addresses in these memories, basically treat them as 2 separate memories, so that all of the even addresses go in one, and all of the odd addresses go in the other. And those, again, are words because these are 32 bits wide. So if you look at the address, 2 bits go to specify the byte within the word in each of these banks. The next bit up goes to choose which of these banks that word resides in, and that's the sense in which these are even or odd addresses. And then the other bits left over go to choose a particular word within those banks. The nice thing about this, especially if they're separate and independent banks, is that in fact they can operate simultaneously. So if the cache misses, it can give instructions to both memories at the same time to fetch an even word and fetch an odd word, and to almost double the bandwidth into the cache for refilling the line. Now it's almost double because in fact the cache can't read more than 32 bits at a time in. It's only a 32-bit wide memory. So let's see how to draw this. Let's say that it takes 100 nanoseconds to read from bank 1 in the memory. At the end of this time, you transfer to the cache word 1. If you start bank 2 at the same time, then it's going to be available, its data is going to be available at the same time. The cache can't read it at the same time, so it's going to have to read it a cycle later, a cache cycle later. So one way to envision that is that we started the access to bank 2, let's say 10 nanoseconds later, if 10 nanoseconds is the cache cycle time. DYCL8 type. We have 4 words to read in, so we do 2 more like this. And basically it takes 210 nanoseconds to fill the line. So it's slightly more than half what it would have been if we had not done interleaving. So with no interleaving, of course, in the original scheme, it would have taken 400 nanoseconds. So it's not quite as good as making it twice as wide, but it means that the cache is only 32 bits wide instead of 64 bits wide. I guess I've said everything we need to say there. Questions about that? Okay. Burrowing in a little further, and I don't want to go over this in great detail, but I think you ought to understand, at least in some level of detail, how the memory chips themselves actually work and what people are doing to make the chips themselves be faster. Most of the dynamic random access memories use a scheme that was invented back in 1974 by Shustek to supply addresses to the chips in 2 parts. Basically, you take the address which is being fed into the RAM chip, you divide it into an upper part, a row address select part, and a lower part, which is a column address select part. And instead of giving all of those bits to the chip at one time, you give half of them during one cycle and half of them during another cycle. One of the main motivations for this, certainly back in the old days, was to reduce the number of pins that were on each of these individual ICs. You halved the number of address lines. So what would typically happen is that you would set up the address line feeding into the chip, and then you would raise a line called row address strobe that says that the row address is ready. And the chip internally would memorize the row part of the address. And you would change the address to be the column address of the location you wanted and raise the column address strobe line. And then sometime later the data would trickle out. For the old original Shustek chips, I think there were 6 bits of row address select, 6 bits of column address select. There was a data inline, a data outline, a row address select, a column address select, a power, and a ground. So that's 2, 4, 6, 18 bits, 18 pins altogether on a chip. One of the other characteristics of these dynamic RAMs is that the data is basically stored on what represents a leaky capacitor. And if you leave the data in there for too long without referencing it, then it degrades. So one of the things you've got to do is that every once in a while, where every once in a while is something like every 2 milliseconds, you've got to read out the data and refresh it, recharge the capacitor, so to speak, put the charge back on them. And that typically represents an overhead of about 2% of time which is inaccessible to the cache or the CPU because the RAM is somehow doing its own internal refresh. Various later schemes elaborated this and allowed some of the refresh to be hidden in processes that go on inside the chip while allowing concurrent access from the CPU or from the cache. Now these are DRAMs. The static RAMs are typically a lot faster. They don't have this refresh problem, so you don't have to refresh the memory, but they typically have something like 1/16th the capacity. So almost all of the main memories for modern computers are built out of these dynamic RAMs. So given that main design, what is it that you can do to spiff up this RAM chip to make it run faster? And people have done a whole variety of different things. One of them is to realize that you fetched out an entire row of bits at once in the RAM. There's no reason to do that again if the bit that you're going to access next is part of that same row. So a lot of the chips have page mode, where you do the row address strobe once to get the row. It gets stored in a temporary buffer on the chip. And then you do column address strobes to get the individual bits within the row in any order you like. Modification of that is to basically use column address strobe only as a kind of clock. And every time you clock column address strobe, you get the next bit of the row. That kind of scheme is great for doing cache refills, because you know that the data you're accessing is going to be sequential. So you do the row address strobe once, you do the column address strobe multiple times, and you get the sequential bits for multiple fills of the cache line. Another kind of minor tweak to that is to make the row memory look like static memory, and instead of using any clocks at all, you just change the address anytime you want to get a different value out for the bit within that row. Another kind of memory that people are designing these days are synchronous RAMs, which in addition to, or instead of having column address select and row address select strobes, they're synchronous in the sense that they have a free-running clock into them, which allows them to be internally pipelined, much the way CPUs are pipelined. So you can get overlap between the next row access and the data transfer of the previous row access. Another scheme for making memories faster is basically to put a cache inside the chip itself. In a sense, the row buffer is a kind of cache, but you can consider, and Mitsubishi has chips that do this, consider elaborating that row buffer with a larger cache, perhaps multiple rows. And you may or may not, in cache sense, store the tag information within that chip. You might, because each of these chips is typically a single bit or a few bits of a word, you might consider externalizing the tag storage into a separate tag storage controller or memory controller. It's kind of a way of having the cache half inside the chip and half outside the chip. Let's forget about that for a second.
Is that for systems without caches?
Could be for systems without caches. It could be for systems that have caches that just want the main memory to be faster.
Well,
All of these systems have multiple levels of
help,
caches.
I don't see how that would help.
Well, let's say that you've got two different cache misses. Let's say you've got a cache miss in data memory and a cache miss in instruction memory. You might be able to start filling both caches at the same time using rows that have been fetched out of main memory and are cached in the chip. So you can get single cycle fills into both data cache and instruction cache from the same memory chips and still not have to go through a complete access time on the chip, because the chip itself is caching both the instruction part and the data part that you're trying to reference. It's just another example where putting caches in series is not as silly as it seems. It can still give you a performance increase. Just 30 seconds on a radically new RAM design. Rambus has proposed, in fact, from some Stanford people, I think Horowitz and Mike Farmworld are mostly involved in this, of making RAM chips look nothing at all like RAM chips, make them really look like independent computers that process a transaction. And what you send to the RAM chip is an opcode saying what you want to do, you know, a read or a write or something like that, and operands like the address and the packet size, and have it process those things in pipeline fashion with caches on the chip and very high-speed synchronous transfers in the typical Rambus type chip. You feed it a 250 megahertz clock, and on each edge of that clock at a 500 megahertz rate, it's providing to you, if it's in its cache, words of data or bytes of data. Very novel and innovative technique for making RAMs that have very high throughput. Perhaps not as fast latency, response time, but very high throughput. The other thing that's actually very interesting about this approach is their business model, which is almost as interesting as their technical model. They're trying to do a kind of Dolby thing where they, in the company, I believe, are not actually interested in building the chips themselves, but they're licensing this technology, much the way Dolby licenses their noise reduction technology, to other companies that actually build the devices. I think that's pretty clever scheme if it works. Okay. Any questions on that stuff? The last part of memories, before we head next week into I.O., is a brief look, and I don't think I want to go over it in terribly gory detail, at the 21064, its memory structure, which the book does go over in great gory detail. But it's worth looking at because this particular CPU has almost every one of the kinds of bells and whistles that we've been talking about over the last couple of weeks for making systems like this go faster. Let's just do a quick orientation here. This is the instruction fetch side, this is the data fetch side. So if we look at the instruction fetch side, first we have an instruction TLB, and this is a 12-entry fully associative cache. In parallel with the lookup in the instruction TLB using the higher bits of the address, there's a cache which uses the low order bits of the address. Notice the low order 13 bits of the address, which are the offset into a 8K page, going down into the instruction cache. And this is a 8K byte direct map cache. And remember that because it's direct mapped, and because they don't want to use any of the, they don't want to mix the virtual page number bits and the page offset bits, it can't be any bigger than 8K. So an 8K byte direct map instruction cache. On the data side, similar kind of organization, a translation look-aside buffer, which in this case is 32 elements, also fully associated. Notice that the look-aside buffer for the data side is significantly larger than the look-aside buffer for the instruction side, because the data side tends to exhibit much less locality. And again, an 8K byte direct map cache with a write-through policy. So because they're doing write-through, which means there's going to be a high level of traffic out to the next level of the hierarchy, there's a write buffer here. So things which have to get dumped out of the data cache get stacked up in the write buffer, waiting to go to the next level of cache. And the next level of cache, these cameramen are doing a great job of sort of following my finger around here. The next level of cache is a unified cache, the level 2 cache, external to the chip, which is, again, a direct map cache. In this case, it's a write back cache. And the size varies depending on how many chips you want to put out there. You know, it could be half a megabyte, could be 8 megabytes. Notice that they've done a victim buffer so that things which are getting thrown out of the level 2 cache get saved in the victim buffer. I think this is only one entry. And we talked about why that made sense, in particular for a direct map cache, to avoid pathological cases where alternating references would cause a miss for every reference. So they use that trick. They use the write buffer trick. They use the delayed write buffer trick in the data cache. Remember, we talked about the problem with writing to caches, that you've got to do the tag check first before you do the write, because you might be writing the wrong data. And one way to avoid that is to delay actually doing the write until a subsequent write cycle later on. And that allows you to do one cycle data cache hits. So in fact, they have the delayed write buffer. Let's see, what else? What other of our tricks that we talked about they have? Well, they have an instruction prefetch buffer. Remember, we talked about how one way to make an instruction, a cache go faster, especially a cache that's often being used for sequential memory accesses, like an instruction cache would be, is to, when a cache miss occurs, fill up the cache, but then use your idle cycles to prefetch the next data, which might cause a miss in the cache. So they have that as well. The book goes through this in great gory detail. I, in the next couple of slides, tried to simplify the great gory detail just a little bit And I don't think I'll go through it here, but you can. And I think it's fairly self-explanatory. All the steps are numbered to correspond, as in the book's explanation, to the numbered circles on the diagram, and you can spend a pleasant half hour pointing multiple fingers around the diagram, following the way that the data goes. The bottom line in all of this is, how does it perform? And this is a summary of a figure which is in the book that describes how well it does. This shows what the total number of stalls in the CPU are for the level 1 instruction cache, remember, which is 8K, the level 1 data cache, which is 8K, and the level 2 cache, which is off chip, but in this case was 2 megabytes. Those are summed to be the total cache penalty in CPI, and then there are the other penalties for other stalls in the pipeline, and then a total penalty. Well, if you look at the spec int, the integer benchmarks, things are looking pretty good. The stall penalty in the instruction cache is just over 1/10 of a cycle, 2/10 of a cycle in data, almost nothing in the second level cache. So the total cache penalty as a fraction of the total execution time is only about 1/5. So that's doing pretty well. In the case of the floating point benchmark, the numbers are a little bit different. The instruction cache miss rate or stall penalty is a lot lower, presumably because there are a lot more tight loops. The data cache miss is higher, presumably because it's accessing big arrays that don't get cached as well. Again, the level 2 penalty is almost negligible. But it still overall performs quite well, in the sense that the total penalty for the cache system is only 1/5 or so of the total execution time. However, one could cynically say that a chip like this was designed to make the spec benchmarks run well, and if you run something which is not a spec benchmark, like a commercial benchmark which has a lot of transaction processing and sorting, then things don't quite look as good. And in fact, in this case, there's about a half cycle each, or just under that, for both instruction and data cache misses. And now the total cache miss is getting up to 40% or so of the total execution time of the CPU. So maybe the next set of benchmarks ought to include something that looks like this, so that the next set of processors that come out in 5 years from now will try to reduce these numbers as well. We're out of time. We're out of memory. Next time we talk about I/O.